practical things.
This is the first talk on a little cluster of Melanin talks. Ben Powell, Seth Olson, Bernie Mostert will all be giving their perspectives and their research in this field. They all work with my group and Ross's group at UQ. So what I'm going to do is I'm going to generally introduce the challenges in the field of melanin research, and of course sort of try and frame it in terms of what we understand as condensed matter physicists and also biophysicists about establishing structural property relationships in complex bioorganic systems and biological molecules. Okay, so my group is a soft matter group at UQ, and I want to give a little plug for the Centre for Organic Semiconductor Research, which is a new research centre opening in May. It's going to be headed up by Paul Byrne, who we heard talk yesterday. He's come to us from Oxford, and we were pleased to have him in Australia. Also a little bit my senior research student, Jennifer Rees, who helped me put this together and with a major influence on this work. Okay, so I'm going to start. I'm going to start in about 1950. And I'm going to draw, first of all, a very distinct parallel between, I suppose, the old world of condensed matter physics, which gave us silicon and gallium arsenide and the inorganic semiconductors, and the opportunities, I guess, and challenges of trying to adopt a similar approach to the arena of soft materials or organic materials or bioorganic materials, and the very different challenges that one faces between those two scenarios. So. If you were to look at an organic material, you might come to the conclusion that silicon, in fact, is a very easy material to study. Nice symmetry, highly crystalline. These are some of the problems and challenges that we have in organic materials. Disorder is a very dominant physical and chemical factor. Chemical heterogeneity at every level is a factor that we have to deal with, and we've heard several talks this morning about how small degrees of structural disorder and chemical disorder can change the properties and the functions of a system quite profoundly. Broken symmetry, in the inorganic case, with systems that are crystalline, we have symmetry that can help us in rationalizing and simplifying a problem, and we often lose that particular tool in highly disordered systems. Of course, we have this massive diversity in compounds and structure. You just take the basic building blocks of organic materials, and the propensity of carbon, for example, to form 3 types of hybrid bonding. And all of a sudden you have a massive diversity of compounds and structures from a very small number of building blocks. And also something that causes significant issues is the fact that weak dispersive interactions play a very, very important role in dictating the structure and the properties and indeed the function of many organic and biological systems. And it's a very difficult issue to deal with, especially for principles calculations. Again, there's been some discussion of that over the last couple of days. So what motivates us in studying organic systems? Well, really, my group is a materials-based group, and we're motivated by the desire to design and to make new materials and devices out of organic systems with applications such as organic photovoltaics, and some of you would have read one of our students' posters at the back, plastic electronic sensors, organic circuit elements. So that's the kind of applied, funky end of things. And of course, there's this imperative as well. It is when you're studying a bioorganic material, your basic bottom line is to understand some biological process, some biological function. And what I'll be talking about today is the biological processes involved in melanin biosynthesis and its function. I'm not going to talk about it today, but the implications, for example, for skin cancer and human photoprotection, which is the main role of these systems, they are directly implicated in the development of melanoma skin cancer. So if you live in Australia and you're Caucasian, you've got a 2 out of 3 chance of getting skin cancer during your lifetime, and of that you've got roughly a 1 in 10 chance of it being a quite nasty melanoma. So this is a big issue for us down there. And any of this type of work, as you would know, is a very, very multidisciplinary effort. It's reflected by the people in the group: condensed matter physicists, quantum chemists, and many body theorists, microscopic people, device physics, and importantly, the synthetic people. Good science starts with good materials, okay? And good materials often start in this field with a good synthetic organic chemist. So that's the grouping of people that we've assembled at UQ as a basic foundation for doing this type of science. Okay? And it's a blueprint that many other big centres around the world are trying to achieve as well. Okay, so this is the basic theme. It's about establishing the structure property jigsaw puzzle. Now, I was very interested to read in the papers that came with the conference booklet some words by John Hopfield. The word function doesn't exist in physics. It's not there, is it? But physicists need to learn about it, otherwise they will be playing in a sandbox by themselves. And I think those are quite profound words. And it has been nice, especially this morning for me, to listen to people who are founded in the real world of proteins, for example, where you have a functional system where the function is intimately related to everything else. And in fact, if I gave this talk 2 weeks ago in a different form, and I had the word function put on the end here, because I was speaking for the School of Biomedical Sciences at UQ. And so, for me anyway, the function is part of this entire jigsaw puzzle. But for today, we'll focus on structure, property, function. Okay, and the human pigmentary system specifically, which are these group of compounds known as the melanins, which I'll describe. So, just to set the scene, I suppose, this is a common mapping that will be pertinent to proteins or DNA or other types of biomolecular systems. Structure at the primary level, of course, and we've heard something about this today. The so-called trivial level structure that some people call it is dominated by quantum mechanics. The covalent bond, of course, is an inherently quantum mechanical quantity, and that's what we teach our undergraduate students. The secondary structure is where you begin to see this quantum mechanical classical crossover in properties at the sort of nanometer scale. And of course then the tertiary structure of proteins, the tens of nanometers, where classical physics really becomes the dominant type of physics that one needs to consider. And all the way up to the aggregated structure on the micron scale, where again classical physics dominates. And we're sort of interested at this end of things primarily, and trying to understand how the primary and secondary structure are related to each other, and what are the mesoscopic linkings between these two things. Okay, so in terms of properties, well, the things we're interested in, obviously at a molecular level, we want to understand the Rex geometries, the electronic structure, the energies of the structures, the phonon structure. At the mesoscopic type of level, electron-phonon interactions, spin dynamics, the delocalization of the electronic wave function, and of course these 1.5 to 6 week dispersive interactions, which are all important in biological macromolecules. And the macroscopic observable, which is the thing that we start off with often and map our way back. We see a property because we're inherently optical things, and we try and explain it. So the optical properties, the electrical, the photochemical, and the chemical properties, things we can measure in the lab quite simply, or send a student off to do it anyway. So a little bit of background about these molecules. The melanins. A class, and it is a class, and a rather large class in fact, and one has to keep that in mind whenever you talk about these systems. A functional class of biomacromolecules, and they really are ubiquitous throughout nature. Here's the giant Australian cuttlefish, which is a beautiful example of an organism that uses melanins and pigments to its own advantage. First of all, it uses it as a camouflage, so the squid can change the colour of its skin locally within a couple of seconds to match its environment. Also uses it for protection. If it gets a bit scared, it opens up its mouth and spits out some black goo, and that black goo is in fact eumelanin. It's sepia melanin, which is very, very closely related to the type of melanin that we have in our skin and in our hair and our eyes. Okay, so those are very similar classes of materials. There are several dominant types in the biosphere. Eumelanin, and it's the one I'm going to talk about today. It's the predominant form in humans. It's the dark brown-black pigment that many of us have got large amounts of in our skin and hair. I don't, for obvious reasons. But if you were to have a very dark hair colour, then it's about 3% by weight of eumelanin as the pigment system in that hair. Okay. Pheomelanin is the red and brown stuff. Ginger people have got a lot of pheomelanin. I tend to have a little bit in my skin because I'm Northern European. Neuromelanin is found in the brainstem, the substantia nigra of the human brain. It's a dark colouring, and there are all sorts of things going on there that we don't understand. But it turns out when you begin to get neurodegenerative diseases like Parkinson's, that the percentage of neuromelanin in the substantia nigra is suppressed. We don't know why, whether it's a cause or in fact the result, but anyway, there's a lot of work going on in that. And the lower melanins are found in the lower order organisms, which are very simple compounds that you find in bacteria and the like. And what got me interested in these things back in about 96, 97 was the rather exotic physical chemical properties that I was beginning to observe in them. Very broad monotonic absorption in the ultraviolet and visible. I'll show you that in a second now. But it's very atypical for an organic chromophore to have such a broad and featureless absorption profile, as many of you will know. I started measuring electrical properties of these things in a solid state and found they have very high levels of conductivity at room temperature, a characteristic for the amount of disorder that they have, in fact. And they're also photoconductive. You shine visible ultraviolet light at these things and the resistance drops. Again, quite strange properties, considering what they are. Something we've come to rather recently is very, very efficient non-radiative relaxation of photoexcitation. So, of course, that is intimately related to its photoprotection. In comes a photon, and that energy is dissipated in a very, very efficient manner. And I'll show you some data on that as we progress. So this thing we're going to talk about, and what the guys are going to talk about over the next couple of days at melanins, they are macromolecules of indole-quinones, for the purists amongst us. And here are some of the very, very important questions and the big challenges in the melanin field. Firstly, what is the appropriate and correct secondary structure? I mean, the whole of molecular biology is founded upon the fact that you have an accurate idea of what the secondary and primary level structure of, for example, a protein or DNA is. A kind of Watson and Crick paradigm of molecular biology. What are the appropriate microscopic models linking this structure to the macroscopic observable if you have a structure, or what's the appropriate model to link that forward? Are melanins quantum materials? How do the macroscopic properties emerge, and at what length scales are the quantum effects important? And this is a very important question, and I guess links very closely with the whole ethos of this workshop. How do the answers to these questions help us understand function and, in fact, the disease state? If one begins to understand the molecule at the most fundamental level, how could one use that knowledge to cure cancer in a basic way? Okay. And as I said at the start, we've got an alternative motivation in this, in essentially molecular engineering of these systems. If you understand these things, then you can begin to understand how to dial in property and how to dial in function for all sorts of reasons. That's where our synthetic organic chemists come in once again. How do we make this stuff? Well, melanin is a basic macromolecule of two components that we know of. Dihydroxyindole, so it's a dicatechol of the indole, and the two carboxylated form of the molecule. There is a significant amount of debate amongst the community as to how much of this and how much of this appears in each type of eumelanin. But in sort of sapien melanin, for example, there's about 30% of this and about 70% of that. In human eumelanin, we think there's rather less, maybe 10 to 15% of that, and the residual amount of that. So there's some debate as to how much of these things there are. Eumelanin forms from these two monomers via oxidative polymerization. We have three possible cross-linking sites which predominate. The 2 position also in DHI is possible for cross-linking, and you form these extended, some may call heteropolymers. I like to use the more generic phrase of a macromolecule, right? And that's what it looks like, and that currently is the state, I guess, of our knowledge of the spectral primary structure of these molecules. You'll notice that the intermediates through the polymer are ketonic states. So the 1 electron and 2 electron oxidation of these molecules is the pathway by which these things polymerize. If I make DHI in the lab, or my synthetic chemist makes DHI in the lab, under any form of oxidative condition, even air, these things will polymerize up into a black compound, which is melanin. So DHI is very reactive, and the only way to stabilize it is either to block these groups here. For example, if you methoxy block these things, the reactivity goes down, or indeed just keep the thing inert once you've made it and try and do everything in under nitrogen on the vacuum. So, challenge 1, structure. So here we have what appears to be a almost randomly cross-linked macromolecule building block. And the sort of pervading theory in the field about its structure is this. And this comes from many, many decades of work as far back as 1960, when the first papers were published on melanin, the first quantum chemical predictions of what the properties of melanin should look like using Huckel theory and various other basic models. And from that, everybody was absolutely convinced that this thing was just an extended heteropolymer of indoles in a similar way to an extended conjugated polymer, and that all the properties were derived from that. And we'll come back to that in a second. So we would call that an extended heteropolymer. We have something which is, maybe 10 or 20 or 30,000 Daltons big, a big, cumbersome, big, heavy polymer. A bit more recently, people have begun to question that paradigm. In fact, as recently as the sort of early to mid 90s, and it came out of a little piece of Sachs work, some X-ray scattering work, where people started seeing spectral functions, structure functions which were consistent with rather smaller elementary units, and so people started beginning to think that these were in fact smaller oligomeric systems, and one can start to consider that when you have these small planar oligomeric systems, that they begin to stack in some sort of way. But I'll return to that a bit later because there's no definitive evidence for that. Okay, so that was challenge 1, which was basically solve the structure problem. Challenge 2 is the optical properties. Explain the optical properties, please. And here are the rather strange optical properties that we have to explain. First of all, here's a simple plot of wavelength versus absorbance from the ultraviolet up to the near infrared. This is the UVA and UVD regions up here. You can see that it's a monotonic increase in absorbance down towards the ultraviolet A and B, and of course that is consistent with it being a photoprotectant functionally, but rather strange for an organic chromophore, one would say. You can plot this thing on a log length scale and you get something which is linear straight lines, so it's a very simple exponential, or down near it anyway. And no chromophoric peaks in this smooth profile, which for anybody who's studied proteins or any other organic chromophores is a bit strange. If you're interested, you can have a little look at this. This biophysical journal last year talks a bit more about that. And if you then look at the emissive properties, the fluorescence properties of these things, the first thing to say is that there's a very, very, very low radius of quantum yield. I mean, seriously low. And of course, that again is consistent with the photoprotective properties. A yield much, much less than 0.1%, so it's hardly measurable. In fact, it's quite a challenge to decouple the fluorescence from all of the other effects that are going on there when you have such low rate of quantum yield. But we've developed methods in order to do that, to subtract away inner filter effects and reabsorption effects of the emission, for example. I mean, you can imagine that when you start pumping this thing here, and you've still got a significant absorption coefficient out here, that the Stokes shifted emission is going to be quite heavily absorbed again. So this is a particular challenge in a chromophore. You can't just move outside the absorption band in order to do this. This is quite a difficult problem. The other thing that you'll notice, of course, and spectroscopists amongst us will say there's complete violation of the mirror image symmetry between emission and excitation. There's no correlation whatsoever between the shape. I know I've plotted this in energy and I've plotted this in wavelength, but there's no correlation between the two things. The emission, in fact, looks somewhat like a normal chromophore. You've got a nice inhomogeneously broadened line shape, Gaussian. It looks very much like you would expect, and the full width at half maximum is not ridiculous either in terms of an organic chromophore. So there's something going on here which is not correlated. And so there's the first big question: how does one draw the comparison between these two apparently dichotic events? And even more strangely, if you look at the behaviour of the monomers from whence the macromolecule came, they behave in a somewhat more normal fashion for organic chromophores. If you take DICA, for example, then you've got some symmetry breaking, mirror image symmetry breaking, because of the and in fact you can read about this in Jack's comms that Seth is going to talk about in his paper. But they behave rather more systematically and much more like a nice chromophore is expected to. So that's challenge 2, the optical properties that we have to explain. Challenge 3, the electrical properties. I mentioned that these things conduct electricity. Bernie Mosted's going to be talking about this in about about 35 minutes, so I'm not going to spend much time upon this, apart from to say that we have a very, very anomalous electrical conductivity behaviour, and I'm glad we talked about hydration states of biomolecules a little bit earlier, because I won't steal Bernie's thunder, but protons are again in biology, and non-ohmic behaviour of the IV profile. Okay. So, three problems. We have the structure problem, we have explaining the optical properties, and we've explaining the condensed phase electrical properties. I'm not going to talk about photoconductivity, that's a whole new ball game. So we'll restrict our discussion to this. So, the current paradigm of how one would go about explaining these properties. So, as I said, for maybe 4 or 5 decades now, the consistent theme has been that in fact this solid state is an amorphous semiconductor. It's an organic form of silicon hydride. And if you make that assumption a priori, then when you make a DC electrical measurement, or you measure the Seebeck effect, or you do Hall measurement, then in fact you can start to convince yourself that you can back out activation energies and solid state band gaps and create some sort of density of states. And this is a typical density of states derived from DC conductivity measurements of something that looks a bit like silicon hydride. You've got a high density state on the Fermi level. You've got a nice trap state tail, both the valence and conduction band edge, typical amorphous semiconductivity picture, and it comes from the fact that, or it's perceived to come from the fact that we've got these indolic units which are linked together. You've got a highly delocalized pi system, which gives you the type of extended structure that we see here. Okay, so that's the basic model, but does it explain the properties that we observe? And that's the question one always has to come back to, I think, in trying to map out this jigsaw puzzle. So the extended indoor heteropolymer, delocalized pi system, amorphous semiconductor band structure, that indeed would give us the broad absorption. And if you map the absorption profile of silicon hydride, one sees an edge and a broad profile and no chromophoric bands. So in some sense it can, and you would ask yourself, well, where's the band edge, the solid state band edge? I don't see it. One could say it's out in the infrared somewhere here, or one could also say, well, the system is in fact particulate, and you've got some mice scattering out here which hides the band edge. And those are all arguments that have been used to sort of sweep that little issue under the table. But we're relatively happy that this picture explains the broad absorbance. The electrical properties, well, under this picture we would have ohmic behavior on voltage and current, and as Bernie's going to talk about it a bit later, we see non-ohmic behavior at relatively low voltages, and that's not consistent, so we'll put a cross there and a smiley face there. The emission behavior, well, unfortunately this does not explain the violation of the mirror image rule that we see here, and it doesn't explain the fact that this now looks like a normal organic chromophore. So we've got to put a cross there. And the other electrical behavior, which Bernie's going to talk about, which is a conductivity which is very highly dependent on hydration state, that doesn't explain that either. So that's the current paradigm. Now what I'll do for the next 5 minutes is explain maybe where our thinking is. And this will help introduce some of the work that's set, and then I'm going to talk about it as well. So, challenge 1, the structure problem. Do we believe that this is an extended heteropolymeric system? Is the question that I'm posing. And I suppose I did for maybe 5 or 6 years, because coming out of solid state physics and organics, one would instinctively assume that that was the correct model for a system like this. We began to question that about 3 or 4 years ago. And I question it even more now after some work we've done in the last 6 months. There's some transmission electron micrograph images that were acquired by a colleague of mine at Oxford. And this is of synthetic melanin that we made in the laboratory under biomimetic conditions, and then did some high-resolution phase contrast TEM. Now, it turns out not to be particularly easy to do high-resolution phase contrast TEM on carboniferous materials. The reason being is that your electron contrast is pretty uniform, so you've got to work really, really hard to get structural feature out of it. Anyway, our collaborators at Oxford are good at this. They do carbon-based materials, buckyballs, for example. And what we begin to see, and I hope you can see it on the, yes, you can just about see it, is that we have planes, concentric planes, appearing to consist within what looks like an onion structure. Looks like a particle with concentric rings. Now you can ask yourself, well, how is this structure organized? How did it self-assemble? Is it, thank you very much, is it a process whereby it's part of the preparation process, for example? So once you've done all those tests, well, I'm going to come to that in a second now. There's a 5 nanometer scale bar. Okay, so if you do the Fourier analysis of that image to see what the dominant spatial dimension is, you find a dominant spatial dimension of around about 3.9 angstroms. And of course, those of you who've done a lot of work on pi stacking will say to me, aha, that's interesting, because the dominant pi stacking dimension is around about 3.4 to 3.8 angstroms. And so what we appear to have here, anyway, the first cut, are these indole planes in a pi stacking configuration, a concentric pi stacking configuration. You can also then ask yourself the question, what happens if we disrupt that pi stacking? So let's test the pi stacking hypothesis and put some pi stack breakers in there. And if you do that, you come up with a structure which is completely amorphous. You break the structure down and you lose that 3.8 to 3.9 angstrom spacing. Now this looks like any other type of conducting polymer which is amorphous. Okay? The next question you ask yourself is, well, that was synthetic melanin, Paul. What about the natural stuff? And this is melanin that was extracted from the eye of a cow, the bovine epithelium melanin. And you also see these concentric indole stacks, again with a 3.8 angstrom in this case, spacing dimension. So these are some quite interesting early observations that might lead to suggest that that in fact that second model I showed you could be more appropriate. But I won't dwell on that right now. So, challenge 2, optical properties. Well, we're already questioning that paradigm of it being a heteropolymer. And the new theory, and again, I'm not going to dwell on this because Ben will talk about this in some more detail, is how one explains this broad absorbance. Of course, you can accept the semiconductor paradigm and say that it's a transition between a set of continuum states that's got a gap between them. Or indeed, if you start thinking about melanins in a more broad sense, and that is maybe as ensembles of chemically distinct species, it's quite easy to model, and in fact we have done so, this broad absorbance by a superimposition of a number of distinct chromophoric species. I mean, this is the ultimate in chemical disorder in a biological macromolecule, and if you do the quantum chemistry, you can work out that in fact it takes a very small number of species in order to build up this broad profile. In this case, we put a standard inhomogeneous line width in there of about 60 to 80 nanometers, and 11 independent Gaussians will fit this very simple exponential. And in fact, we're now beginning to identify the species that exist at these particular lambda maps. Okay, we call that chemical disorder, where the macroscopic property is the ensemble average of a number of chemically distinct species. Do you see this elsewhere in nature? The humic acids show a very similar type of property. Humic acids are just basically natural junk. They're the decay products. But that's strange because humic acids really are junk. They're not functional molecules in that sense. What we have here is a biologically functional molecule or set of molecules that were designed for a very specific purpose. So you could draw that parallel, but really you'd say that humic acids are a very cool cousin. In the interest of time, I'm going to skip over this, but the basic hypothesis for that chemical structural model is going to be some quantum chemistry that Ben is going to talk about a little bit later. Okay? And as my last slide before summary, I want to give a little Plateausette's talk on Thursday, which is going to talk about a piece of computational work that was done and will be published in JACS hopefully very soon, about proton transfer and about the role of protons in defining both the optical and electrical properties of these systems. So I won't dwell on that. Seth will pick up on it. Okay, I'm going to summarize now. Key objectives in all of this work: establishing the structure-property relationships, the 3 challenges, correct secondary structure, optical properties, electrical properties. Current theory, the conjugated heteropolymer model, leading to amorphous semiconductivity, is not really consistent with some of the electrical and optical data, so one has to question that. Our current status as we work, the structure, well, I think we're getting reasonably convinced now that we're seeing stacking and self-organization in these systems. That would not be consistent with a heteropolymeric model because of the number of degrees of freedom that one has in that structure. It certainly means that you've got to have confined two-dimensional organization in the system. You've got to confine the system in 2 dimensions to get that stacking, as you do with most aromatic systems. Chemical disorder appears to be a very plausible hypothesis for the optical properties, and we now think the proton transfer, and Seth will talk about that, is an important issue as well. And Bernie's going to talk about the system in terms of electronics and proton transfer. So I guess I'm going to finish there. But I would finish with a particular question for those that are sort of biochemical bent amongst us, and that is to think whether this degree of extreme chemical disorder, and it is there, and we're fairly convinced it is now, is a generic feature of this system, and whether it's a generic feature that we see throughout other biological macromolecules which have some functionality. Now, Elmarsh Cruz from ANU stood at that point, so stuck his hand up, and you have as well, and said there is some disorder in the PS systems, and that disorder is very important. But we're not talking about small amounts of structural disorder here. We're talking about extreme chemical heterogeneity at the most basic level. Starch, is it a functional molecule?